So, good morning. Welcome to Krishna's classroom. We continue with the part B of strategies to modify Riemann integral. That leads to the path to Lebesgue integration. In fact, we have explored a part of it already, and we found that the strategy appears to be to work on the range and divide it into subintervals and then pull them back to the domain. Then whatever sets you get there, you want to attribute a length to each. At the same time, we were also wanting to have the so-called length that we attribute to the sets that emerge from it be such that if they are intervals, then it should coincide with the length of the interval. This was the strategy. So let us just go back through the strategies that we had. The first observation was that f can be written as f plus minus f minus, where both f plus is positive, f minus is positive. Of course, f is defined from R2 or some subintervals of R. Right? So we are talking about real valued functions, all right. Now, this essentially tells you that, and the integration that we have from our experience is Riemann integral. We are going to extend this. Therefore, whatever integral that we end up with is going to inherit the property of linearity, which means that integral f, let me write d mu or dm or whatever it is, equal to integral so it is sufficient to work on non-negative functions. The only catch is this, that we are now not restricting our choice to bounded functions, right? And also the domain, we don't insist that that's going to be bounded. So what happens is that it is quite possible that both integral f plus dm and integral f minus dm may be plus infinity. Okay, and in fact, this is the definition of f. F is considered as an extended real value. What does it mean? R plus R star we are taking as R union plus infinity union minus infinity. That means the points at infinity also has been included into this. We will work on the rules of the game, like what is addition, what is multiplication, etc. in the extended R star soon, but we can extend it from R to R star. That we will do. And in that case, you are likely to get plus infinity for both f plus and f minus. And in that case, you see, you end up with infinity minus infinity. And for such functions, we will say that it's not defined. Otherwise, even if one of them is infinity, the other is finite, the integral will be finite. So that's the only caution that you have to make. Therefore, in the second stage, we assume that f is non-negative, f is from or some domain, some subset of R to R star. That means it can possibly take infinity, plus infinity also in the definition. And we develop this for this class of functions, integral. Then you can certainly extend it using one. That is the start. What did we do? See, for Riemann integral, we were working on bounded intervals AB, so the graph of the function is somewhere here. What we did was we divided the domain into a collection of disjoint intervals, and we had a partition of AB, that is P, the partition P x naught, A equal to x naught, x1, n intervals, where n could be any integer. And then suppose this is xi minus 1, xi, we approximated the area enclosed between the curve, the ordinates at xi and xi minus 1, which is a region of this type, and we approximated it from below and above. Below, by taking the infimum of f on that interval and then working out the rectangle with built on the interval xi minus 1 to xi with height, what you call the mi. So this height taken as mi, which is the minimum or the infimum of f on this interval. And then we also had another approximation or another rectangle approximating it from above with capital Mi as the side of this interval, and then you had this rectangle. So you have the area enclosed between the curve and these ordinates is now approximated from below by this rectangle as well as this rectangle from above. It's squeezed between those two. And similarly, it happens everywhere. Okay? And then you see that the lower approximation is going to be given by, with respect to this partition, is going to be given by the step function, which is defined as S. What do I call it? I call this Sn sigma mi, the characteristic function of the xi minus 1 to xi. Plus The last one we will do from xn minus 1. So it starts from a to x1 and so on. So you will have plus mn closed interval so that's a lower approximation subordinate to the partition P, or I can write here as P. And I have an upper approximation, and this runs from I equal to 1 to n minus 1. And the upper approximation is by another step function, namely SP x equal to sigma I equal to 1 to n minus 1 mi chi plus n minus 1 x included, yes, where you see that mi is equal to supremum of and mi, small mi equal to infimum of xi minus 1 less than or equal to x less than or equal to x I of x. We are taking f to be non-negative. Okay, so you have two approximations, and you see that the what you have is this SP now what we do is we define the integral of these two. Okay, the integral of this is essentially, so we write integral of this is equal to what you have, the mi sigma mi into x1 integral this is defined as sigma so this is the lower integral and upper integral. Therefore, what you have is this, that this is what is called the upper sum. This is called the lower sum, and this is called the upper sum. So you have the upper sum and lower sum. And then we had this, what you call the lower sum, and you see that if you take the usual thing, that is if P prime is a refinement of P, then you see that the lower sum will increase. And if P prime is a refinement of P, then the lower sum would decrease. Okay, so this is what you have. If then this is what you have, sigma the integral whatever is that, and you have this one less than or equal to integral s p prime this is the inequality that emerges. So with refinement, the lower sum would increase and the upper sum would decrease, and you see that the set of all lower sums is anyway bounded by this, and this is what you can do. Integral sp x p1 is less than or equal to for any partitions P1 and P2 that means all the lower sums are bounded above and all the upper sums are bounded below. So all the and the lower sums so you produce some real numbers, a set of real numbers which is bounded above and a set of real numbers which is bounded below, and if at all the function is integrable, that integral is a number that lies between the lower sums and the upper sums. Okay, so you take the supremum of the lower sums exist, which you call the lower integral of f. So we designate now supremum of designate as lower integral of and infimum of over all partitions P upper integral of this is the lower integral and this is the upper integral. They exist. The upper and lower integrals exist. If they are equal, then we say f belongs to is Riemann integrable of AB. And now this was the definition. Okay, so we were approximating by a sequence of step functions. This is the important part. This small sp and capital SP are step functions. So we are approximating from below and above by step functions. And the step functions get closer and closer to the function as we increase n, and from both from above and from below. And for step functions we have defined what the integral is by simply adding the areas of the rectangles involved. Okay, and then of course using the power of analysis and making use of the properties of these collection of SPX and capital SPX for over all partitions, the limit exists, and then you call the supremum of that of over P small sp exists, infimum over all P of capital SP integral capital SP exists. They are the lower and upper. So everything is fine, and if they are equal, then everything works. Now the problem we found was that we were not getting sufficiently many functions as Riemann integrable, and especially if you were to define a linear space of this RAB with a what you call the L1 norm, then we found that you see that with all the technical niceties that we have to exercise at this stage of constructing an equivalence class of functions, you define an equivalence relation over this class of RAB and then find what you call the integral of the equivalence class and so on. With all those things, we find that the space that you get eventually is not a complete metric space, and therefore the Riemann integration that we have developed is not strong enough to catch hold of several functions. Okay, and it is not possible to do analysis safely on RAB. That was the problem. It is in this context that we went for remodifying. And then of course, as I explained last time, our strategy is now to do something different. Different but very similar to what we did. Okay. I think I explained everything in the last lecture. So I'll just simply say what I did. Once again, the strategy is to approximate the function through step functions. But now in a different way, in such a way that you can catch hold of more functions into this class. Let us take the same picture, but you could have extended real valued functions to work with in our new scheme. So I'll just, to demonstrate what is happening, I'll just take the same graph and then see what you do. Okay. Yeah. Okay. Let me do this. It's not necessarily true that you have to be working with the continuous functions or anything, but for explaining what is going on, we'll use this graph. Okay. Now, instead of dividing the domain into disjoint intervals, we start working on the range. Okay. We subdivide the range. So you shall call this x-axis, this is y-axis, and then you see you have yi minus 1 to yi. Let this be an interval. Okay. No. Can keep the graph like this to bring more clarity. What I do is, I have an interval yi minus 1 to yi. Okay. And so the function f, this is y equal to f of x, the graph of this function, or you see that any point on this is the ordered pair x, fx, where x belongs to the interval. Now what we do is the following. We are going to find out the pullback of this interval onto the domain. What is it? Let us get the pullback. Here there is a small region which gets pulled back. There is another region which gets pulled back into, and then again this is. So you see that from our figure, these three regions are going to be what I call F inverse of I minus 1 yi, this set. Okay. So instead of working on the domain, I work with the range. Okay. And then pull back intervals or y intervals into the domain of the function using the function. So function is now going to have a role in deciding what is the pullback, as it is clear. And you see that on this set, that is f inverse of yi minus 1 yi. See, a approximation from below is given by a step function. I'll write down the path. So you see that here what I do is on this set I take the value of the step function to be equal to yi minus 1. And if I mark this region, shade it out, this becomes an approximation, a lower approximation or approximation from below to the desired area trapped in this region. Okay, right? So what you have is this. So you have now, okay, let us write down. So the sort of function that we define is this. You will write Sx to be sigma I equal to one to infinity. What I have is this. The value of the function is yi minus 1, the lower value, multiplied by the characteristic function of f inverse of yi minus 1 yi. That means a function that takes the value 1 over these sets and otherwise 0. This is the characteristic function of this set. Multiply that by the lower value of the interval, that is yi minus 1, and then sum it up. Okay, so you get what you call a step function. You can easily see that when two intervals here are disjoint, their pullback are also disjoint. So note that disjoint intervals of the range inverse image f disjoint. That's an observation. That means if two intervals you take, say something like say you take any interval of this one. Suppose that is empty, then f inverse of yz intersection f inverse of y tilde This is also okay. This is one observation that therefore you see that since all these intervals yi minus 1 yi, that is closed open intervals, they are disjoint for various values of I, you see that their pullback are all disjoint sets. So you end up with disjoint subsets of AB, and you can take the characteristic function of that, multiply by the lower value of that interval, and then sum it up. You get a step function. This is what is called a simple function, or the which gives you a lower approximation. Once again, you see that in this portion, this is approximated by this line. This is approximated by this line. This is approximated by this line. And if you take another interval, then it is going to be a different story. So for each such thing, there is a pullback, and these pullbacks of distinct or disjoint intervals are disjoint sets, and for each of those sets you can define the corresponding characteristic functions, multiply by the lower value of the interval, and that forms a lower approximation to the function. Now you see, why not the upper approximation? See, the upper approximation, the difficulty is that we are likely to have the function taking the value plus infinity on some subset of it, which we are not going to get ruled out. Okay, it may be a set of points where the function becomes unbounded. That can happen. We are also giving room for that, and if that happens, then you see that the upper approximations will turn out to be probably having some taking infinite values and so on. So it won't give you a approximation, or you won't have the limits working properly. Here one thing is certain that while working, as we shall explain it later, these step functions are bounded above by the given function. Therefore, the corresponding integrals that you can define possibly is this integral Sx. Now this is the problem. Let me call this Tm for the time being. I will explain what it is. This is equal to natural way in which you work on this. What happens is, this is going to be the sum yi minus 1 multiplied by the length of f inverse yi minus 1 yi. Okay. What do we mean by length of a set which is not an interval? So the question is, this is one of the problems that you immediately encounter. The length of sets That's one of the basic questions that you come across. See? So we have to attribute some meaning to this. Okay? We don't know because we have length defined only for intervals. Okay? For intervals it is well defined. But what happens if it is not an interval? Then what you get? That's a question that we have to encounter at this stage. So that provokes, because in this case what happens is the pullback, that is f inverse of yi minus 1 yi for the function that we have drawn there, consists of the union of three intervals. It's not a single interval. The union of three intervals. And therefore, we have to give some meaning to what we mean by the length of this set. And obviously, what you do is, you try to define the length as, this is where you have to define the length as sum of these three intervals. Okay? So that's a way out. So in the present example, f inverse of is a union of three disjoint intervals. For this particular I, if you take a different interval, it may be even empty set. Okay, for some value of I, it may be what I have marked. It is clearly this, but if for a different I, it may be even an empty set. That is possible because you see that if I take this interval for instance and look at the pullback, where does it go? Doesn't intersect the graph of the curve. Therefore, you see that the set of points which gets mapped through this function into the range or into this interval is going to be an empty set. Okay, so that can happen. Depends on how you choose this. Okay. In this particular case, define the length of f inverse of yi to be the sum of the three intervals making up this. For instance, suppose I look at this one. So suppose f inverse of equal to I3, where I1, I2 are pairwise disjoint. Then we take I'll keep this figure there. Length of f inverse of to be equal to length of, say, I1 plus where okay. So it is possible to do this if they are simply disjoint intervals. So disjoint intervals sometimes you will get, but last time we have seen a function where this pullback may not be a interval at all. There are situations or union of intervals, disjoint intervals, at all. For example, this we have considered last time. Consider f to be equal to the characteristic function of 0, 1 intersection 2. What is this function? This function is 1 at all rational points in the interval 0, 1. And this function is 0 at all irrational points. Okay. So look at the pullback of this function. This I have explained last time. If you are taking the interval in the range to contain 1 then the pullback is going to be all rational points on the interval 0, 1. And if we are taking the interval to contain 0 but not 1, then you see it is going to be the entire set of irrationals, and they are not intervals, they are not even union of intervals. Okay, now this is the problem. If you want to accommodate these kind of functions, you have difficulty. And then what do you mean by the length of such sets? Okay, so let us write this down. Because I cannot draw the graph of this function, because at all rational points it takes a value. This function takes the value 1 at all rational points. In 0, 1, and the value 0 all irrational. This is a Dirichlet function. So you see that this is what you get, F inverse of is equal to empty if 0 or 1 does not belong to yi minus 1. This is equal to the set of all rational points if 1 belongs to this is equal to complement intersection 0, 1 if for that I equal to Q complement intersection 0, 1, that means the set of all irrational points if 1 does not belong to yi minus 1 yi, but 0 belongs to yi, and this is equal to the interval 0, 1 if both are in so this is the scenario. You could have 4 situations. If the interval does not contain both 0 and 1, then it is empty. If it contains 1 but does not contain 0, then it is going to be the set of rational points in the interval 0, 1. If it does not contain 1 but contains 0, then it is going to be the irrational points. And if it contains both 0 and 1, then it is going to be the whole of interval. So we have to deal with 4 types of sets. Well, if this is of the first type, then we can probably postulate the length to be equal to 0. If it is the 4th type, then of course we can postulate the length to be equal to 1, the length of the interval. But what to do in between? That is when it is the set of all rational points and when it is the set of all irrational points. So I will just write down here. So the problem is this. If F inverse of empty, we shall postulate or we shall define length of equal to 0. That looks perfectly fine. And if F inverse of yi minus 1 yi is the interval 0, 1, then you define length of But for the other 2 cases, what do we do? Two scenarios. This is the question. At the outset, you don't know what to do, really. Okay? Right? Therefore, let me now list out the problem. So our task is set out now. So our task is this is the task. Define arbitrary subsets of the domain. The sets may not be intervals or union of intervals as in the previous case. Example. In these cases, there is a way out. The way out is a natural definition of what we mean by the length of an interval or the length of a set of disjoint intervals. Okay? But if your set does not fit into that, what to do? This is a question. So we have to define or extend the notion of length to arbitrary subsets. Okay. The second problem is, of course, is it possible do it all subsets of if not, do it for as large a class subsets as large a class of subsets as which includes all intervals and union of in such a case we know what to do. Okay. They are disjoint intervals, it's a union of disjoint intervals. Then you certainly define it as the sum of the lengths of these intervals. That we know. But in general, you cannot do it. We have already seen the example where it fails to do. So, we don't know at the moment, we have absolutely no clue what we do with it. Okay. So, this is the central problem. Okay. Now, at this stage, we'll introduce the question. So, the measure of the Okay. So this is our task, to define what is called the measure a subset wherever it is possible and wherever it can be sensibly done. But it should be a class larger than the set of intervals or union of disjoint intervals. Okay, that's our objective. Okay, suppose we have overcome this part and we have introduced what is called measure of a set. Okay, and it's a different question whether you can do it for all sets. May not be able to do. Okay, maybe that you may not be able to do it for all sets. So what do we do in those circumstances? This is the question that we come across. So let us see what we can possibly do. Suppose we have overcome this barrier and this task we have performed successfully. If so, what to do? Assume we have overcome this barrier. That is, we have successfully defined a sensible measure for a large class of subsets of the domain F. Which includes all intervals and union of intervals. Disjoint. So for this you have a way out, but for that you have to work it out. Okay. Just designate. Let A be a subset of domain. Okay. And assume measure of A we call is different. We could successfully define this for A, or A is a subset for which this is well defined. Then, what are things you need? The check is this, that is, if A is an interval, Then we would like measure of A to be equal to the length of A. Now A is an interval. That is, if A is of the form some alpha beta this way or any way, whether it is open, closed or anything. So A is some interval I, some subinterval. Then measure of A, length of, this is what you, that is the way in which you get back to the Riemann integral situation where you come across intervals. Okay. And then you can extend that to disjoint intervals by postulating that the measure is going to be the sum of these lengths of these intervals. That is the strategy. Okay. But how to go beyond that? I mean, that we have to work out. Some difficulty or some work has to be done. So we observe a few things. What is the measure? The measure is going to be a non-negative number that we associate with the subsets of the domain of F. Okay. So the measure is going to be M of A is going to be something, a number greater than or equal to 0. Okay. Right? And we would like to have, so this is the property that we need. If you take all sets on which it can be defined, suppose I call, okay, suppose script A be the subsets of the domain of F where each element A of has the measure defined. This M of A is a real number. Then what we have is this 1 M of A I am cautious here. I am taking the largest collection on which I can define MA subject to the condition that this is true. That is, for intervals it becomes the lengths. Okay. 2, what we expect is that if A is equal to A1 union AN, where AI intersection AJ is empty, then measure of A It is finitely additive. So you see that it's a set function defined on A. So measure is now a map from the collection of subsets into you would keep it also infinity because you have the interval, the whole interval. Then, from minus infinity to plus infinity, you would like that length to be equal to infinity also. Then, first of all, it should be non-negative. M is non-negative. Finitely additive. Okay. Then it should be countably additive. In the sense that if AI with which is pairwise disjoint, okay, then you would like what we like is this, that measure of A should be right. So that property has to be true. Then we want possibly the properties of length being preserved. That means measure of A has to be equal to I, the length of I, if A is equal to I. This is the length of I. That means if it is something of the form, if A is an interval, then its measure is the length. Further, you also know that you have this property. For any interval I plus x is an interval. I plus x is defined as this I plus x. Now we see that for an interval, length of I, length of I. Length of I. So the length is invariant over translation. That is, length is a function which is invariant under translation. So we would like the same property for the measure. So we would like M to be a translation invariant function. That means, that is, if A belongs to A, you would like A plus X and A plus X belongs to A, then measure of A should be equal to measure of So we want the measure to be a non-negative function, which is countably additive. For intervals, it should give you the length of the interval, and the measure should be a translation invariant function. So these four properties that we are asking. Okay, right? So this is what is called countable additive. Property, then fifth law. So these are the desirable properties of the measure function. See, measure is a non-negative function defined on a class of sets. Okay. Now I am going backward. From the requirement, I am trying to find out what A should be. What should be A? So A should have some structure. A is a collection of subsets of the domain of F. Script A I am talking about. Okay. Now first of all, and possibly maybe the sixth property, we would like empty set belongs to script A. And the domain of these are the two other properties. And maybe we would like the measure of C. For example, for the intervals. Okay. Right? Take an interval of the type x, comma x. X is there, but x is not there. Okay. And it's an empty set. And for that, you know that the difference would give you the length. Okay. For even a singleton set, which is of the form x, for any interval. So you see, all sorts of nice properties should be there for your function. So your function is not any arbitrary real valued function that you are talking about. Okay. So that is our task. Right? So we have our task very clearly set. Okay, that is the following. Take the domain of the function on that, on as large a class of sets as possible. You define the measure. Measure has to be a non-negative extended real valued function. Okay, and on empty set it should be equal to 0. For intervals it should be the length of the interval. Okay, and it should be translation invariant. It should be countably additive. All these nice properties have to be there. Okay, so that's what we are looking for, and that obviously demands a certain structure on this collection of sets. If it is the whole, all the subsets of I, then you are happy. Okay, so let us not commit at this stage. If it turns out to be the whole, all the subsets of the domain of the function f, then we are extremely happy. Okay, but you don't know whether you can do that with so many constraints that has been laid out now. Okay, with such a lot of constraints that we have laid on the function, still we hope that at least on intervals, yes, we can do that. So it will contain all intervals. We can legitimately do it on all intervals that are there. But then you have to go beyond that. Okay. So can you do it? How large a collection of sets you can get on which this can be done? And such a class is what we have denoted by script A. Okay, right? Now, therefore, script A should be amenable to the sort of things that you do. What is that? Empty set should be there, the whole set should be there. Then, what more? Union of sets in, desirable properties are union of sets in A are or what you call countable union of subsets of script A should be an element of A. And you also would like to have intersection of or countable intersection of subsets of A should be in A. What more you need? You need, if you have a set A, then its translation should be in A. That is, if A belongs to A plus X belongs to A, and the measure of A is equal to A plus X. That condition should be satisfied. Actually, all intervals are to be there and so on. So, you need some structure on this class of elements so that the preconditions required for defining a set function having all the desired properties of length is there on A. So that's the one. So A has to be a class of subsets of the domain of A. Sorry. Where measure of A can be comfortably By what I mean is that, okay, another property that you need is if A is in A, if capital A is in script A, then A complement also has to be. So that is another property. These are all the desirable preconditions that you would like the script A to satisfy, so that you can comfortably define such a function if at all it is possible. I mean, there is a lot of constraint here, like countable additivity is a big constraint to fix in. Then, of course, a lot of special features that you demand for this function. Okay, and you want essentially the measure to be defined as a legitimate extension of the concept or length for intervals. That is what it is. Okay, suppose we have achieved that. Okay. Suppose we have crossed this barrier. That is, we have defined M for a large class of domain of F. Okay. As large class as possible. Satisfying all these requirements. Then what can you do? Now you see, you can define integral of S. With respect to this measure, can be now defined as the following: sigma I equal to 1 to infinity y I minus 1 multiplied by the length of this set. Measure of F inverse of So you consider this as an approximation to the integral of it. Okay. Now you can define what is the integral. See, these are all areas which approximate from below. So one thing that you observe is this: if we refine the intervals, by splitting into subintervals. Okay, and call the refinement. Okay, then we see that the corresponding step function. Corresponding step function is greater. Okay, let me make this clear. Right? So let us draw a diagram. We make this point clear. Okay. This is the lady just giving a picture of what happens. Okay. Now what we do? We are doing the following. Take yi minus 1 to yi. Look at the pullback. What is the pullback? The pullback consists of this interval, and then this interval for the particular function that we have. Going to be these three. And then the approximation that you make is the graph of Sx is going to be this, or one portion of this will be this. This is approximated by this one. But suppose we introduce an intermediate. Okay. Suppose I introduce an intermediate. Zi. Then you have, look at the pullbacks of yi minus 1 zi and zi to yi. Okay. So you see that this is the line I have to draw. Now you see this part where you define the function approximation by the same quantity. But then on this portion, you define this as zi. I hope you get the point. Okay. So let me write this here. Minus 1. The characteristic function of f inverse of this is it. What you suppose we refine it with some zi's in between. Then what happens? Between yi minus 1 and yi. For every I say, or for some I, whichever way you want. Okay. Then what happens? Then you see that yi minus 1 yi is essentially equal to yi minus 1 zi union zi so what we have is this, that some point between yi minus 1. Then what you observe is this. See, you write down the corresponding function. So suppose s tilde x is equal to sigma I equal to 1 to infinity. yi minus 1 chi of f inverse of yi minus 1 yi plus zi plus zi times chi rather than writing it cramped. So I take s tilde x, I define as sigma I equal to 1 to infinity yi minus 1, that is the lower value of it, chi of f inverse of yi minus 1 zi plus zi times sigma I equal to what can you say about the relative position of these two functions? quite easy to see that Sx is less than or equal to S tilde x. So it's a sort of refinement of the step function Sx. Then what you have is this. You see the integral is equal to sigma one to infinity. There are all sorts of convergence problems, etc. are there. I am not ignoring that. I am just formally writing everything. Y minus 1 times measure of the interval or of the set F inverse of yi minus 1 yi. This is it. Okay. Integral S tilde is going to be sigma I equal to 1 to infinity yi minus 1 measure of F inverse of S inverse of yi minus 1 yi plus zi here, intermediate point here it is, plus zi into m of F inverse of zi yi. This is it. So this is the sum that you are going to work with. Okay. So that corresponds to two sums. One on this set and the other one on this set. On this set, the value of the function is zi. On this set, the value of the function yi. Okay. So it is now clear. Now it is clear that means every refining will get you another approximating step function. Okay, and that function approximates to the function much better, as it is clear. See that instead of approximating this function by this one, instead of approximating it by this one, you are approximating by this one, this one, and this one. This is the scenario that you get. So you get a much better approximation. Okay, right? So you see that this inequality is true. Therefore, through refinement, you can get a monotone step functions. And it is bounded above either by the integral or this. So what you get is that you have a sequence Sx and Sx is monotonically increasing and Sx, at least it appears, converges to Fx. And therefore we define integral Fx dm to be equal to the supremum of all over all Sx dx, supremum taken over all S less than or equal to m. These are all simple functions or step functions that you. This would be our strategy to define the integral. Okay, right? And if it works, we call that the Lebesgue integral of f. That is approximating f from below through step function. Now it is quite possible that this supremum becomes infinite also, because we are not taking f to be bounded. Not assumed to be bounded. Bounded. Integral f df may be equal to that's also possible. Okay, so this is the strategy that we adopt. This is exactly like in what you call the Riemann integration. Okay, in Riemann integration also we had two things. One, approximating from below by a class of step functions, but the step functions were very restrictive class because they are associated with the partition of the domain. And approximated from above by a set of step functions. Here this is more versatile. Okay, because we are getting a partition of the domain through a partition of the range and the given function. So the given function has a role to play. And that is the important part. That is why we get an edge. And of course, it would be certainly quite a task to prove that all Riemann integrable functions are Lebesgue integrable and the Riemann integral is equal to the Lebesgue. So I just stop here. Okay, maybe make some more noise about it in the third part of this series of, this lecture on strategies. After that, we will systematically build or go through our task. That will be the development that we want to take up. Thank you very much. I hope you enjoyed my lecture.